Okay, so this is a video about chain rules as they apply to partial derivatives. If we kind of recall, the original idea of a chain rule is that if I have some function y, which is an f of x, and a function x, which is a function of t, then I can take what is the derivative of y with respect to t, and I can find that by taking the product of the derivative of y with respect to x times the derivative of x with respect to t, right? So this is kind of one way of formulating that, right? We're going to build off of this to get the idea of a partial derivative, a chain rule for partial derivatives. Okay, so let's take a look at how that works. Okay, so there's a couple of different types of problems that can come up here. We'll call this type 1 problem. And in this type, you have a function f, which is a multivariate function. Could be of any number of variables. We're going to make it of 2 for right now. And then those variables themselves are dependent upon some value t. So both variables are dependent upon the same value. So it's kind of like parametric here, right? So x and y, both dependent upon t. Okay, so if this is the case, this is very similar to what we just did. We're going to say, well, what is dz dt? Now notice that this is an ordinary different derivative, right? So this is the straight up and down d's, not the curly ones. And the way that we end up getting this is by taking the partial of f with respect to x times dx dt. So this one is a partial, this one is an ordinary derivative. And then we're going to add to that the partial of f with respect to y, and this time dy dt. So this is going to give us the derivative with respect to z as I'm going through t. So this is only a single variable function, right? So z is ultimately just dependent upon t. As t changes, how does z change? Well, using this sum of kind of like two partial chain rules. So let's look at an example of how this works. Let's say that z is x squared y plus 3xy to the fourth, and we're going to let x be equal to the sine of 2t, and we're going to let y be equal to the cosine of t. Alright, so we need a couple of things here. We need, let's see, dz dt, right, is going to be the partial of z with respect to x. So let's see, what do we get there if we do that? That should be 2xy plus, let's see, 3y to the fourth. And then we're going to take dy dt, or dx dt, which is 2 cosine of 2t. Right? And then we're going to add to that the partial of z with respect to y. So that's going to be x squared plus 12xy to the third. And then dy dt is going to be negative sine t. Okay, so keep in mind that we're going to try to find the value of this when t is 0, right? So let's keep in mind that when t equals 0, right, this is going to make x equal to, let's see, that's going to be, sorry, x prime, right? No, x is the sine of 0, which is 0, okay, and y is going to be the cosine of 0, which is also now 1, right? Okay, so let's start doing some substituting in. 2 times 0 times 1 plus 3 times 1 times 2. Let's see, this is cosine of 0, so that's going to be 2 times 1 plus 1 plus 0 for x, right? 0 is x. There we go. Plus 12 times 0 times what is going to be 0 times negative sine of 2. That's 0. So we really have to look at this. This goes to 0. So this is really just 3 times 2, which is 6. Okay, so what we got here is that if this is the setup, then at time 0, every time t changes by 1, z is changing upward in the positive direction by 6. So this is going up pretty quick. Okay, so as the particle is tracing this path on the floor, so remember it's like a three-dimensional reality, x, y, z, so this is going to be some sort of curve on the floor, right, from t equals 0 to t1, whatever's going on here. This value is how this thing is going up and down as it's following that path. Right, and at time 0, it's going up. It's going up by 6, so it's going up steeply. At time 0, as it's following the path in the positive direction. Okay, so there's another possibility here that kind of flips this around a bit. So we'll call this a type 2 problem. And the type 2 problem is a little bit different, okay? So in the type 2 problem, we still have a multivariate function. So f is going to be xy. But x and y themselves are going to be multivariate. So x is going to be determined by s and t, and y will also be determined by s and t. So in this case, the best that we can hope for is two partials. We get a partial derivative of z with respect to s, right? And this is going to give me partial z with respect to x times partial x with respect to s, and then partial z with respect to y, and partial y with respect to s. So now all four of the factors here are going to be partial derivatives. And likewise, you can get a dz dt, which is partial z with respect to x, partial x with respect to t, plus partial z with respect to y, partial y with respect to t. So this gives me the two partial derivatives because this function is now ultimately based on two variables, s and t. Alright, so let's get an example for Alright, so let's say that z is e to the x sine y, and x is some st squared, and y is s squared t. It should be pretty straightforward. So the partial of z with respect to s is the partial of z with respect to x, which is just e to the x sine y, times the partial of x with respect to s, which is just going to be t squared, plus the partial of z with respect to y is going to be e to the x cosine y, and the partial of y with respect to s is going to be with respect to s is going to be 2st. Okay, and a little bit of rearranging here. What do we get? We get, let's see, t squared. X is s to the t squared, so that's going to be es to the t squared, sine of s squared t, plus e to the st squared, cosine of s squared t, and that's going to be times 2st. Okay, so now we have the entire derivative in terms of s and t. Alright, so let's do dz dt. Right, so this is again going to be, so these are staying the same, right? So I need the dz dx, which is still e to the x sine y. And this one is going to be e to the x cosine y. So those are not changing, right? But ultimately here, we're going to get, let's see, we're going to take with respect to t this time. So if I take x with respect to t, I get 2st. And if I take y with respect to t, I get just s squared, right? So a little bit of work here. Let's see, I'm going to get 2st e to the st squared sine of s squared t, and then plus s squared e to the st squared cosine of s squared t. So that's my two partial derivatives in terms of s and t. And so that's how we kind of handle a type 2 situation here. So we get a kind of weird application here, and we get a sense where we can use this for implicit differentiation. And it actually gives us a formula to do implicit differentiation using partial derivatives. So what we're going to do is we're going to build, let's say I have a function f of x, and y, though, is also going to be some function of x, right? So we're back to y being f of x. So we have a big f of x is a multivariate function where the first variable is x and the second variable is dependent upon the first. Okay, so we're going to let y be f of x in this case, right? So it follows that if I take the derivative, the ordinary derivative of f with respect to x, I should get 0, because if f is 0, then its derivative should also be 0. So using our chain rule here, right, both of these are dependent upon x, so I should be able to say that this is the partial of f with respect to x times dx dx, so that's kind of interesting, plus the partial of f with respect to y times dy dx, right? So that's going to be equal to 0. All right, so dx dx happens to be 1, right? So let's kind of move this over to the other side. So I'm going to get the partial of f with respect to y dy dx is the partial of big F negative with respect to x. Okay. I'm going to simplify the notation a little bit here. I'm going to say that this is big F sub y dy dx is equal to negative big F sub x. And if I come up over here, dy dx thereby is negative f partial of x over f partial of y. So this is actually going to give me a formula that I can use for implicit differentiation. So, okay, let's take a look at an example of implicit differentiation. Okay, so here's textbook example of implicit differentiation. X cubed plus y cubed is equal to 6xy, and we want to find y prime, dy dx, right? So we say that this is 3x squared plus 3y squared times y prime, right, is equal to, first times the derivative of the second plus the derivative of the first times the second, right? So let's see, what do we do here? We move things around a little bit. We get that 3y squared minus 6y times y prime. Sorry, not 6y. Minus 6x times y prime is equal to 6y minus 3x squared, right? We divide, we get y prime, 6y minus 3x squared over 3y squared minus 6x is going to give us, let's see, divide it all by 3, 2y minus x squared over y squared minus 2x. Right, so that's pretty straightforward. All right, so this is what we got by doing this the classic way without using any type of partial differentiation, right? So let's see what happens if we do this with partials. So our original equation is x cubed plus y cubed is 6xy. We need to set this thing equal to 0, so we're going to let x cubed plus y cubed minus 6xy equal to 0. So we're going to let big F of xy be equal to this x cubed plus y cubed minus 6xy. Now, so according to what we wrote earlier, if I take f sub x of xy, this gives me 3x squared minus, let's see, that's going to be 6y. If I take f sub y of xy, this is going to give me 3y squared minus 6x. And according to what I've read, dy dx, aka y prime, should be negative fx over fy, which is 6y minus 3x squared over 3y squared minus 6x. Divide it all through by 3. We get 2y minus 3x squared sorry, 2y minus just x squared, right, over y squared minus 2x, which is precisely what we got on the other page. You can back up the video and check. So it's just another way of solving the same problem. I think that this is perhaps a little bit computationally easier. It is definitely more abstract. You don't see all the inner workings of the implicit differentiation, but because you're working off of something that's functional, I think it works itself into algorithms much easier, because you can build these functions into code and kind of work from there. So it's another way to do implicit differentiation that comes from these big chain rules that we studied in this section.